we move over to our last presentation by Timo, and he will talk about POES article precipitation dataset and its effect on the atmosphere.
Yes, hello. Can you hear me well?
Yes, we can hear you.
Okay, I'll try to share my screen so you can see the slides. Okay, can you all see?
Yes, we can.
Okay, that's great. Okay, so I hope you are all still awake after a long day. Last presentation. So I come from the University of Oulu, from a space climate research group actually, and we have been using this POES satellite data for a long time. And let me first of all, in the first part of this presentation, tell you something about these satellites and how we have been revising the data set. I think the POES measurements were already mentioned in a couple of presentations, but just for the basics, these POES satellites, they are polar orbiting satellites which orbit like this, as you can see in the animation, about 800 kilometers altitude in sun-synchronous orbits. What makes this data set very interesting in many aspects is because it's very long running data set. They have been operating these satellites since the end of 70s, nearly continuously present up to present. And I think the newest satellite, which is not even included in this time series figure, was launched in 2018, METOP-C. Now, the particle data set, these satellites, of course, measure a lot of different things, but I'm interested in the energetic particles that they measure with the MEPED instrument. Now, MEPED data, of course, is available in the internet, in the NOAA website, all of it, but there are several instrumental problems that plague this data set. Now, over the years, let's say actually it becomes almost like 10 years since I started working on this, and we have been tackling these different instrumental problems. One of these is the fact that these detectors, as they are being operated in the satellites for more than 10 years, for instance, they get old, they suffer from radiation damage, their response changes over time, and we have been developing different satellite intercalibration methods which allow us to track these changes and compensate it back. Then there are also other problems like electronic noise effects and things like these. Also, one problem is that detectors, there are separate detectors measuring protons and electrons, but actually both of them are sensitive to both particle species. So it's a bit tricky to separate true electron counts from true proton counts. But you can try to do that, for example, by simulating the instrument response with certain Monte Carlo simulations. So you build a model of this instrument and shoot particles in there, and that's what we have been doing. And these sorts of response curves then allow us to take in the proton and electron measurements and try to separate the real counts from them. And there's also the additional fact that over time, this satellite program has been using two different versions of these instruments, which have some subtle differences in their instrument construction. They actually changed the instruments here with NOAA 15, and so there's a difference between the blue ones and the red ones, and actually that causes some interesting problems which we were able to solve only last year finally. So many people use this POES data for different purposes. It's become especially important tool in the atmospheric and climate community over the last years, and I will talk about that later on a little bit. But because it's a very vast source of data, we tried to in this study, we tried to somehow simplify it into a homogeneous long-term record, which would be easy to use in, for example, climate simulations where simulations require atmospheric ionization caused by these particles. So there are in constructing such a homogeneous record, there are a couple of things that arise. First of all, by this type of a simplified record, I mean daily latitude distributions of particles, like in this plot. So we have time, southern and northern hemisphere, and then you have the particle counts. This is just one particular example from one of these energy channels and one of the telescopes. So these types of data products we want, you could zoom into these in daily resolution and see all sorts of structure there. But the problem is that you first of all see some funny things, for example, happening in this plot. You see some sudden changes, for example, here, sudden change there, sudden change there. You see some background noise and all sorts of things happening. So in these sorts of, for this kind of a data product, we need to figure out how to get rid of this. First thing that you see is this temporarily changing background, which is due to these instruments being sensitive to cosmic rays. Now that's relatively easy to remove. You can view each of these bins as time series and just trace a background curve there and remove it. So this is something you need to do first. There's also another additional kind of problem which relates to the fact that these orbital planes of these satellites don't stay fixed in time. This plot here, for instance, shows how the orbital plane, basically the MLT, magnetic local time, where the satellite is at the equator, changes very slowly as a function of time. For example, with NOAA 15, it goes like this, with an amplitude of several magnetic local time hours. Now, this is a problem, of course, because the particle distribution around Earth and in the precipitation zone in the upper atmosphere is not constant, but it changes with local time. So if the satellite changes its position where it's measuring, this will be felt as a temporal, very slow temporal change. And it may be mistaken as a temporal change when it's actually a spatial change. So taking a bunch of satellites that we have here, for example, in the year 2000, from 2000 onwards, we have satellites in different kinds of orbits. So we can use them to build up these kinds of statistical maps of particle precipitation, and then using these maps to kind of compensate the change of satellite measurement location, for example, from here to here. That allows us to compensate these types of changes away. Now, there's also another problem which is related to the fact that in addition to changing the instrument construction, these satellites also change the direction in which these particle telescopes point relative to the satellite, relative to the magnetic field. So this cartoon here tries to show, for example, two different versions of this. There's the SEM2, newer one, and SEM1. And these, for example, the 90-degree telescopes are pointing in very different directions. This color plot shows you, for example, if you don't take this into account, you see a very dramatic change here when they start using SEM2 after SEM1. So they make this telescope change somewhere here. Now, fortunately, there are a few years of overlapping measurements here. It is not shown in this picture, but these measurements here actually continue here. Using this overlapping part, we can then use some machine learning methods, which can be figured out essentially to get the mapping from this type of a measurement into this type of a measurement. So figure out how to transform this into something like this, or equally this SEM2 to SEM1 level. either way. Here we have done so that we have transformed this SEM1 measurements, these earlier measurements, to the same level as these newer measurements. And you can see that this inhomogeneity, sudden jump that appeared here is now removed. Just to show you that this is a really big quantity of data that we are dealing. So basically we have 3 energy channels from a 0-degree telescope. These are the untreated ones. These are ones which are fixed with noise and this sampling location and telescope changes. They look much more clean. The same thing with this 90-degree telescopes. So these versions are now something that can be, for example, used either as real data to track, for example, radiation belt, ring current evolutions, or equally well in climate models as input, which create atmospheric ionization and thereby some atmospheric effects. And those atmospheric effects are now the second part of this talk. There's actually been quite a lot of studies on this, and it has been shown that this ionization that energetic particles and auroras cause in the mesosphere, for example, they lead into ionization, of course. This ionization kicks off chain of chemical reactions, essentially, which creates these nitric oxides, hydrogen oxides, and so forth. These have the capability of catalytically destroying ozone. Ozone, of course, is mostly in the stratosphere, much lower than the altitude where these molecules are created. But each winter, during winter time, there's this downwelling in the polar atmosphere within the polar vortex region, which is the descending branch of this Brouwer-Dobson circulation. And that basically brings these molecules down each winter into the stratosphere. In the stratosphere, they can then destroy ozone. And this has been shown both by model studies and observational studies that this happens basically each winter, and depends somehow on the magnitude of this electron precipitation. Now, we have also studied this, and we are mostly not interested in chemistry. Chemistry is also, it's kind of a one block in this chain of events that happens, but we are more interested in the dynamics and how it couples all the way down to the surface of the Earth, into the troposphere. So we made simplistic, relatively simple analysis to understand. So we have this era interim climate data set, which runs from end of 70s up to present, and it contains a lot of different atmospheric variables like temperature, winds, ozone, and so forth. And so we compress the data into these zonal averages, which you can express as a function of latitude and altitude. And in each of these grid boxes, we simply made a regression analysis coupling the variations of this particular quantity into variations of these energetic particles measured by the POES satellites. And here you can see in different winter months, 4 winter months, the response, essentially the regression slope of this analysis. How does this different quantities respond if you increase electron precipitation? What you can see is a decrease of ozone here, both in the upper and lower stratosphere. You see associated cooling of the lower stratosphere in each of these months, and a warming of the upper stratosphere. These temperature changes are in thermal wind balance with the wind, which means that you have enhanced zonal wind here in each of these winter months. And this enhanced zonal wind is related to the, of course, enhancement of the polar vortex, which circulates in the stratosphere each winter. Now, in a very recent paper which just was published, we were able to show kind of some of the details of how this dynamical response comes from this chemical response. So how does ozone loss kind of, what is the chain of mechanisms that ultimately leads into enhancement of this wind? And without going into too much details, we found that this dynamical response is basically present not always, but only during those situations, those kinds of winters when you have lots of planetary activity into the stratosphere. Typically, this planetary activity also at some point during the winter may cause sudden stratospheric warming, which breaks up the vortex, polar vortex entirely. But typically before this breakup, it also, the same planetary wave activity that breaks the vortex allows the electron precipitation to couple into it. And the reason why it couples during these times is because of this elevated planetary wave activity, which kind of dynamically amplifies these initial signals in the temperature caused by ozone loss and radiative changes into this kind of a strong dynamical response. This is related to the wave mean flow interaction. So the idea is that ozone loss makes a small change in the atmospheric temperature winds. These changes in the winds affect the way planetary waves propagate. And planetary waves also can affect the wind by leaving some of their momentum into it. So if the wind changes planetary waves and the planetary waves changes the winds, this may kind of lead into a positive feedback loop, as was shown to happen here. And this is the mechanism how it the dynamics operates.
There are 2 minutes left.
Yeah, I only have a few slides, don't worry about it.
Thanks.
So for a very long time, it has been known, of course, that stratosphere affects during the winter time the tropospheric weather. This is, for example, a plot from 20 years ago, which shows you that when you have for example, a strengthening of the polar vortex, these variations drop down to the troposphere in a matter of few days, maybe weeks. And similarly, if you have a breakage of polar vortex, it propagates down to the ground. So if this electron precipitation changes the stratospheric vortex by these mechanisms, it also propagates to the ground. And we have also seen that it affects in ground weather, basically this wintertime NAO index. NAO index has been, or NAO phenomenon, which is the relative describes the relative strength of these large-scale air pressure centers in the North Atlantic. This type of positive phase of the NAO has been shown to be related to, or a part of it has been shown to come from the polar vortex. So when polar vortex is strong, it essentially causes this kind of a positive NAO phase. And for a very long, actually one of the earliest studies that we made out of this, we showed that this NAO index during the winter time correlates very well with the electron precipitation flux, as you can see here. And it leads into this kind of a temperature pattern, relative temperature pattern occurring in the northern hemisphere. Such a temperature pattern, of course, is naturally caused also by this NAO phenomenon. So if you compare electrons and temperatures, you get similar kind of a temperature pattern as the NAO index would cause. And the reason for that, of course, is that this electron precipitation affects the NAO index with or NAO phenomenon via the polar vortex. And we have also shown, well, maybe I should tell you that we have also studied the solar cycle behavior of this electron precipitation and found out that the major driver of that are the high-speed streams coming from solar coronal holes, which means that they typically peak in the declining phase of the solar cycle. Now, this is a very convenient result because it allows us to make some inferences about past climate observations and past geomagnetic and solar observations. Here's a sunspot cycle going back 150 years. And what we did in this study was to indirectly study the effect of energetic particle precipitation by picking from these solar cycles times which are in the declining phases like this, or equally well in other phases. But the declining phase is interesting because we know that the energetic electron precipitation maximizes in each of these phases. So here what is being shown is for each solar cycle running in the x-axis, the average NA index in the different phases of these solar cycles. And immediately what you see from this figure is this one row here, which is filled with red and yellow color, apart from this one blob here. But anyways, if you look at the statistical average, you can see that something in the declining phase tends to bias the NAO index into being significantly different from zero, actually being a positive value. And that supports the interpretation that also in the past, before direct observations of these particles by satellites, the same mechanism has been operating so that it has maximized in the declining phase, strengthened the polar vortex, and thereby caused this positive NAO index during the winter time in the troposphere. So maybe I'll leave it at that. I just say as a summary that this revised POES dataset is now heavily being used in this climate business. For example, for the first time, it's been included as input in this climate models in the CMIP6 climate model intercomparison effort, and it's expected to lead into some very important and interesting results. And maybe the most important point about these results, just to remind you that indeed this particle precipitation does seem to have effects also on the wintertime weather here, also on the ground level, not only in the thermosphere, mesosphere region. Okay, thanks for listening.
Thank you very much, Timo. That was very interesting. Also related to the coupling to the middle atmosphere, which is very nice.